In this video, we'll formally introduce ANOVA. We're going to start our discussion with variability partitioning, which means considering different factors that contribute to variability in our response variable. For example, at the end of this course, you'll each take a final exam, and not everybody's going to get the same score on that exam. That's expected. The variability in your final exam scores will likely be due to a variety of factors. One of them might be whether or not the student completed all components of the course leading up to the final exam, such as the videos, the quizzes, the midterm, the lab, so on and so forth. However, there will certainly be other factors as well. Familiarity with the material beforehand, number of hours per week put into the course, so on and so forth. Suppose we're interested in studying how strongly completing all components leading up to the final exam is associated with exam scores. To study this, we would partition the total variability in exam scores as variability due to this variable and variability due to all other factors. We're going to build up on this idea of variability partitioning and the F statistic we introduced earlier to work through our way of the analysis of variance output. Let's quickly remind ourselves of the data we're working with. From the general social survey, we had the vocabulary scores, the numerical variable, social class, a categorical variable. We have our summary statistics at the group level as well as at the overall level. Our null hypothesis is that the average vocabulary score is the same across all social classes, and the alternative hypothesis says that the average scores differ for at least a pair of social classes. Let's visualize this idea of variability partitioning. Suppose the circle represents the total variability in vocabulary scores. We partition the variability into two: variability that can be attributed to differences in social class and variability attributed to all other factors. Variability attributed to social class is called the between group variability, since social class is the grouping variable in our analysis, and the other portion of the variability is what we're not interested in. And in fact, it's somewhat of a nuisance factor for us, since if everyone within a social certain class scored the same, then we would have no variability attributed to other factors. This portion of the variability is called our within group variability. Here's a look at the ANOVA output. The first row is about the between group variability, and the second row is the within group variability. We often refer to the first row as the group row and the second row as the error row. The third row displays the totals. Next, we're going to go through all of the values in this table, how they're calculated, and what they mean. Let's start with the column of sum of squares. The last value in this column is sum of squares total, commonly referred to as SST. This value measures the total variability in the response variable. In this case, that would be the variability of vocabulary scores. This value is calculated very similarly to variance, except that it is not scaled by the sample size. More specifically, this is calculated as the square deviation from the mean of the response variable. We have 795 observations in our data set, and the mean vocabulary score is 6.14. So to calculate SST, we take each individual score and subtract 6.14 from it, square the difference, and finally add up all the values. For example, the first observation is 6, so that's 6 minus 6.14 squared. The next one is 9, that's 9 minus 6.14 squared. The third one is also 6, so on and so forth, and we add up all of the values to get to the total sum of squares of 3,106.36. This value represents the total variability in the response variable. But what we're really interested in is how this variability is partitioned into between and within group variabilities. As an aside, we can see that this is an awfully tedious calculation to do by hand, and hence for ANOVA we usually rely on software to do the calculations for us. So the calculations we're going to present in this video are for illustrative purposes and for introducing the concepts, but you'll likely never have to calculate these by hand. You still need to understand what they mean so that you can interpret your analysis though. Next, let's talk about the sum of squares group, SSG. This value measures the variability between groups and can be thought of as the variability in the response variable explained by the explanatory variable in the analysis. It's calculated as the deviation from group means from the overall mean weighted by their sample sizes. So more specifically, for each group, we calculate its mean, that's y bar j, subtract the grand mean from it, y bar, square this value and multiply it by the sample size for that group. We do this for each of the groups and sum them up. Here's a summary table that's going to help us. The lower class group has a mean of 5.07. We subtract from that the grand mean of 6.14, square that value, multiply it by the sample size for that group of 41. We do the same thing for all of our groups and arrive at the sum of squares group of 230.56, which on its own is not a meaningful number, but it's interesting how it compares to the total sum of squares we calculated earlier. For example, this value is roughly 7.6% of SST, meaning that 7.6% of the variability in vocabulary scores is explained by social class, and the remainder is not explained by the explanatory variable we're considering in this analysis. This is a low percentage, which I think would make sense because we would expect vocabulary scores to be associated more with education or how much people read. The last value here is sum of squares error, SSE, and it measures the variability within groups. In other words, this is the unexplained variability, and it's the variability due to all the other variables. The simplest way of calculating this is simply as the difference between SST and SSG. Now we need a way to get from these sum of squares measures to the mean square values. To do so, we need to scale the sum of square values by values that incorporate sample size as well as the number of groups, namely the degrees of freedom. So next, let's focus on that group. Total degrees of freedom is calculated as sample size minus 1, 794. Group degrees of freedom is calculated as number of groups minus 1, 3. And the error degrees of freedom is simply the difference between these two, 791. Next up is the mean squares column, which measures the average variability between and within groups and is calculated as the sum of squares for that component divided by its degrees of freedom. So we can calculate that by doing the divisions. And we're going to next use these values for calculating our F-score, because remember that the F statistic is the ratio of the average between and within group variabilities. In other words, it's MSG divided by MSE. Once you have your F-score, you're finally ready to find your p-value and conclude the hypothesis test. The p-value in this context is the probability of at least as large a ratio between the between and within group variabilities if in fact the means of all groups are equal. This is just another way of saying p-value is the probability of observed or more extreme outcome given the null hypothesis is true. And it can be calculated as the area under the F distribution, and the F statistic has two degrees of freedom group and degrees of freedom error. So the p-value shown on the ANOVA table is the tail area under the F distribution with 3 and 791 degrees of freedom, which is tiny. Note that even though we're looking for differences, we only consider the upper tail of the F distribution. This is because the F statistic can never be negative. Think about it. It's the ratio of two measures of variability that can't ever be negative either. Since the F statistic is always positive, a more extreme statistic will always be more extreme in the positive direction. Even though the ANOVA table always reports the p-value, if you wanted to do so, you could directly calculate it in R using the PF function. This function takes the observed F-score as one of its arguments, as well as the degrees of freedom, and we need to note that we don't want the lower tail, and get this tiny p-value, which is indeed less than 0.0001. Now it's finally time to make a conclusion. If the p-value is small, we reject the null hypothesis and say that we have sufficient evidence for the alternative. If the p-value is large, we fail to reject the null hypothesis and conclude that the data do not provide convincing evidence that at least one pair of population means are different from each other. The observed differences in sample means are then attributable to sampling variability or chance. In this case, we had a pretty tiny p-value, so what's going to be our conclusion?